Today, we're going to talk about remote visualization on compute Canada clusters. So why remote visualization in the first place? Well, I assume that you have a large data set that you want to visualize. Presumably, you generated that data set from a numerical simulation that you ran on one of our clusters. And the data set could be very large. So for example, many time-dependent simulations have hundreds of or thousands of time steps saved to disk. And each time step could be anywhere from several gigabytes to several tens of gigabytes. So we're talking overall, about multi-terabyte size data sets. And obviously, downloading such data sets to your computer is not a good, a good use of your time. So what you want to do, you can probably leave the data set on the cluster and analyze it remotely. Even for smaller data sets, if you manage to download it to your computer, it might just not fit into your computer's memory. So most personal computers these days have anywhere from 8 to 16, maybe 32 gigabytes of memory. And your data set, if it's larger than that, you won't be able to analyze it comfortably. Right? So in this case, you can also do remote visualization. And on a cluster, the nice thing is that not only our nodes have much more memory than the numbers that I just mentioned, you can also analyze your data set in parallel. So you can decompose it and analyze it so spread it in memory across several compute nodes. And that way you can analyze very large data sets. Also, rendering on your computer might be just too slow. If you're analyzing and trying to render a data set that is multiple gigabytes in size, then you will hit limitations in your CPU and GPU power. An added benefit of remote visualization is if you have a very large data set, then you want to analyze it in parallel, and you can read it in parallel from multiple compute cores and multiple compute nodes. And if your data set is in one of the compatible formats, then reading the data set is actually going to be much faster. Reading it in parallel is going to be much faster than serial read as well. And obviously, you cannot do that on your own computer, but you can do that quite easily on the cluster. And in the in this talk, I'm going to spend 5 probably minutes talking about compatible file formats and how to decompose your data set so that you can benefit from parallel I/O. Also, several special use cases that I'm not really going to talk about today. So in situ visualization is also kind of remote visualization, and it refers to instrumenting your simulation code in such a way that it outputs graphics directly. So we're not going to talk about it today. It's probably a topic for another webinar. Web-based visualization with data sourced from a remote location. This is also a different topic, and we touched upon it briefly in several previous webinars, but I'm sure we'll revisit it again. Also, a case where your visualization software that you need to visualize your data set is either commercial software and we have a license for it, or for some reason, maybe you cannot run it on your computer. So in that case, you can actually run it remotely on our clusters. In any case, in this webinar, we're going to talk about remote visualization. So your data is on an HPC cluster, and you want to visualize it remotely. So it turns out that you actually have quite a lot of choices. You can do visualization interactively inside a remote desktop, things like VNC, X2Go, other things. So I'm going to show you a slide about these. Also, you can do, for supported software, you can do client-server visualization. This is by far my favorite way of doing visualization because it gives you visual interactivity. So you have a feeling that you working with a local data set, whereas all heavy-duty rendering and data analysis is done on the remote cluster, usually in parallel. And finally, batch visualization. So batch visualization refers to visualization when you don't open any windows at all. You write directly into a file. Also, you might have to choose between GPU visualization and CPU visualization. And for your chosen hardware, you typically have also a choice of several ray tracers and rasterizers. So I mentioned a few of these in this talk. You might want to do your visualization in serial or in parallel, depending on the size of your data set. And one of the questions that I'm going to talk today is how much resources you want to dedicate to a visualization, how many CPU cores and how much memory. So this is also something very important that you should know. And finally, debugging. So even for remote data sets, very large data sets that you cannot download to your computer, you can do debugging remotely or locally using a proxy. So by proxy, I mean a smaller resolution copy of your data set that you can download much easier to your computer and write a script for it, and then copy the script to the remote cluster, and then analyze the full-size data set there. All right, so I'm going to start with batch rendering. So batch rendering is probably one of the easiest options. And also I want to start with batch rendering because there are lots of tools that people use for plotting, things like Matplotlib, other Python libraries. And typically these tools open a graphic in a separate in a new window. And a lot of folks think that this is the standard way of working with these tools on remote systems as well, which is not true. You can actually, from all of these tools, you can render directly into a file or into a movie and then download this in a separate step. And this will be much faster than opening remote windows. So again, batch rendering is an off-screen rendering. Which means that either you type your commands from in Linux or Python shell perhaps, or you are running a script. Typically, it's going to be a Python script, right? And the script you can run either interactively in the login node, you can run it interactively inside an interactive job that you submitted with Salog, or you can submit it as a regular batch job with as batch. So all the usual benefits. So when we talk about batch rendering, usually batch rendering is done with scripting. And all the usual benefits of scripting apply here. So with scripting, you can easily automate mundane or repetitive tasks. For example, if you have a large time-dependent data set, you can interactively visualize one of the frames, one of the time steps, and then write a script and then apply the same script in a loop to all time steps, and that will produce a nice movie at the end. Also, scripting lets you document your workflow, right? You can run the same, you can save your script and then run it maybe 6 months later, or pass it to a colleague of yours who can also run it on his or her own computer. And of course, scripting is really great when you want to do visualization on remote systems, because with scripting, with batch visualization, you don't open any windows. So it's much easier to do visualization from the command line. So it turns out that workflow in pretty much any Linux compatible visualization tool with any sort of programming interface, whether it's in a compiled language or interpreted language like Python, can be fairly easily scripted on a cluster. So I'm going to show you several examples of batch rendering, and then we're going to jump to more complicated interactive client-server VNC and other workflows. Here, this slide shows you some examples of tools that have scripting interfaces. And popular Python libraries like Matplotlib, Plotlib, Boca can all be scripted from Python. YT Python library for multi-resolution volumetric rendering is really great. I really like it, and I'm going to show you an example in a few minutes. Various domain-specific tools, for example, Visual Molecular Dynamics provides both Python and TCL interfaces, and there are several other tools that I don't mention here. So if, for example, you have any domain-specific visualization tool with script that supports scripting, and you are wondering how to use it with scripting for batch visualization on a cluster, just send me an email and I'll be happy to help you. Also, a number of general purpose visualization tools. So VTK, the usual suspects. So VTK is a very popular library for scientific visualization and computer graphics. It has interfaces in several different programming languages, including JavaScript and Python. So it can be used as a standalone renderer from these languages. MyVI is similar to Paraview and Visit, except that it's much simpler. It's not parallel, it's serial. But it also has embedded Python shell. Blender, very famous open source ray tracer for 3-dimensional modeling, animation, etc. And also, and of course, Paraview and Visit. So in this talk, I'm going to spend most of the time talking about Paraview, but let me start with several simple examples showing you Matplotlib, Plotly, and YT. Because all these libraries that I just mentioned, they're Python libraries, you need to start with a Python setup. And the way we recommend doing this on a cluster, on a compute candidate cluster, is by initializing, by building your own virtual environment. And this lets you isolate the specific version, install specific versions of software that you want, and all of these versions will be sitting in a single location in one of the directories in a home directory, and everything will work very nicely. So the way you do this is typically you load the version of Python on the cluster, the version of Python you want. So here's an example of one of the latest Python 3 versions. And then in this case, I also load an MPI for Py module. So MPI is the message passing interface library for Python. And I need this one specifically for parallel rendering in YT. So in one of the examples I'm going to show you in a few slides. And then you create your virtual environment, right? So you create a virtual environment that is going to be put into a home into one of the folders in your home directory. So in this case, I decided to give it name Astra, but the name could be anything, and it's just going to be a folder inside a home directory. Then I activate this environment. So this activates Python and some other tools. One of these tools is the Python package manager pip, and you use it to, so first of all, you upgrade pip itself because it might be slightly out of date. And then you install the libraries that you want. So you want, in this case, I installed just a whole bunch of libraries, matplotlib for basic plotting, also plotly for basic plotting, numpy, math library, and then h4py, so that's the HDF5 library for Python. And then I install YT as well. Right, and then anytime, so after this installation, you can log out, and then when you log in, all you need to do to load these environment is simply run the source function, right? Source on Astra been activated, and that will load Python with all these libraries. So you can drop into the Python shell, or you can run the script by passing the script name to the Python command. And then in this case, also load MPI for Py, because if I want to use it with YT, I need to preload the module before loading the Python environment. At this point, are there any questions? I will pause for a second to let you ask any questions. Feel free to unmute yourself if you have any questions about the Python environment or anything I mentioned so far. All right, well, I don't see any questions, so let's continue. In this example, I'm going to show you a matplotlib script that creates a remote visualization. So in Python's matplotlib library, there is a notion of backend. So backend is basically the target for your output. So you can save your output, your graphics inside a PNG file, inside SVG vector graphics, PDF, PostScript, and a few other things. And then inside your script, so you want to initialize this one of these backends, and then obviously at the very end of the script, you want to save your image. So if you're curious about Python backends, all links in these slides are clickable. You can just click on this link, and it will give you much more information. Also with matplotlib, in case you are not familiar with this package, it's been around for almost 20 years now. Very popular tool for simple 1D, 2D, and a little bit of 3D plotting from Python. So there is a gallery page where you have hundreds of examples of various visualizations with matplotlib, and then you can click on any of these visualizations, and it will give you the code behind that visualization, so you can use it as a template in your workflow. All right, so here's an example of a batch script. In this batch script, I'm just asking, it's a serial batch script, so I'm not specifying the number of processes. That means it's going to be serial, just one CPU core. I'm asking for 5 minutes. 1,000 megabytes of memory. So typically for small visualizations, you don't need a lot of memory in matplotlib. Then you have to specify your actual account, right? So you have to replace this with your own account, your own allocation on a compute canal cluster. And then I source my newly built Python environment, and then I run the Python script called triangulation.py. And here is the triangulation.py, so the entire working script, where two things, as I said, are important for off-screen rendering. One is you have to enable the off-screen rendering targets. In this case, it's a PNG backend called AG for some reason. I don't know why in the story behind this in matplotlib, but this will let matplotlib render into a PNG image. And then you build your visualization. So in this case, I'm just creating a simple plot with Delaunay tessellation. And then this strip color command will actually do the plotting. And then at the very end, I save it into a PNG file, right? So with this done, your PNG file will sit on the cluster file system, and then you can easily secure copy it to your own machine for viewing. All right, so here's another simple example, this time with Plotly library. So Plotly is very similar to matplotlib, except that it supports in-browser plotting, interactive plotting. So when you create a plot in Plotly, unlike with Matplotlib, where you have a PNG, with Plotly you have it creates a web page, dynamic HTML5 web page, where when you load it into a web browser, you actually have some instruction. For example, you can move a cursor, it will show you a current point under the mouse cursor, or or things like this. So very basic interaction. Also with 3D graphics, you can actually spin it, rotate it in 3D, and so on. So Plotly is open source and is kind of free. So it's entirely free if you work offline, if you create your own images, which is what we want. We want to create a remote file on a cluster. And of course, they have a paid hosted version if you want to use the hosting. So here's an example of a code. I call it parametric.py, and all it does is visualizing this parametric curve, which is done. Well, the entire Python code is right here. So there are two important things again. First of all, you want to enable offline plotting, so you have to load the Plotly offline module. Right? So this will let you plot into a standalone file. And also at the end, when you do plotting, so you specify the file name, it's going to plot into file parametric.html. And then you must specify this order open force flag, so that Plotly doesn't try to open a window when it creates the graphic. It just renders directly into a file, right? And so when you run this, well, actually, this is a script, and the way you run the script is you're going to say Python parametric.py, and you can do it either interactively on the login node if you don't use a lot of resources, or you can submit it as a batch job. So submitting to this as a batch job, you will just modify this example script, right? So now it's just going to be a different code. That's the only change you're going to make here. And it's going to create a graphic, and then you can create this. You can download this HTML file to your machine, and then I'm actually going to show you what it looks like. So it's going to create this HTML5 web page that will look similar to this. Let's see if it loads. Yeah, here it is. It's just a little bit slow with the Zoom running in the background. So here we have an interactive web page, right, which is just a standalone HTML5 that I created on a cluster and then downloaded it to my machine. All right. So the final example with relatively simple plotting is with YT. So YT is the three-dimensional data analysis and visualization package for volumetric multi-resolution data. Initially, it was written for analyzing galaxy formation models done with ANSYS simulation code. But actually, in recent years, it saw some use in other fields other than astrophysics. So people in seismology, geophysics, nuclear engineering, molecular dynamics, earth sciences also started using it, and it's really nice tool because it's a Python library that can just put it into your code and then run it inside on any machine, including a remote cluster. And it does all sorts of plots, so volumetric plots, slices, projection plots. Really nice. You have full control over the color map. And a couple of years ago, I gave actually a couple of webinars. So if you're interested on YT, if you're interested in this, you can visit this page. bit.ly/these pages. And with this tool, so here's an example of how you would use this tool in parallel. Here's a script called grease.py. And here I enable parallelism. So by calling this function, I turn on MPI parallelism for YT. And then I load some data set. So it's a free data set that I can load from this website, the data website in the YT project. And it's just some sample galaxy formation model, cosmological model. And then you create a scene and you create a graphic. And what I'm doing here is actually, you can see a loop. So there are 900 loop iterations. So I'm taking my visualization and I'm spinning it by 180 degrees over 900 frames. So this script is going to create 900 images. And then I'm going to merge these images into a movie. So here to run this, I actually asked for CPU cores, so that's why I wanted to enable MPI-style parallelism, and I asked for 12 hours maximum runtime. So creating 900 frames actually takes a little bit of time with YT. And here's the entire job submission script. So I load the MPI4Py module for parallelization. I load my Python environment, and then I just run the script. So srun make sure that this script runs in parallel. So here's just some testing. timing. If I run the script in serial, it takes, well, in 1 minute, I can render roughly 1.5 frames. If I turn on parallelism with 4 CPU cores, I can do roughly 4 frames in 1 minute. So you can see speed up from parallelization. And then when the script finishes running, it will produce 900 PNG images that you can merge into a movie with the tool FFmpeg. And these flags, they sound complicated, but actually give you, so I found that this combination of flags gives you very high, very nice quality, very portable MPEG-4 file, so QuickTime compatible, other things. And it will encode all these frames at 30 frames per second. So with 900 frames, your movie is going to be half a minute long. And then you can just download. So we have FFmpeg installed in our standard environment on all classes, and then you can just take this movie and download it to your computer using either CQ copy or async or FTP, any of the secure FTP programs that you like using. So here's an example of this visualization. You can access it on Vimeo. I'm actually going to play it on my machine. So I'm going to say open, and it's called grades.mpeg4. Not sure if it plays smoothly over Zoom, but we'll see in a second. But it's just a nice visualization that was created entirely remotely on Cedar cluster. Okay. Just like a small logical volume with subgrids highlighted. All right. Okay. So unless there are questions, let me continue. I don't see any questions in the chat yet. Today, we're going to talk mostly about Paraview and a little bit about Visit. So Paraview and Visit are the two tools for very large scale visualization. And these tools are known to scale to very large size data sets, gigabytes to terabytes. And that means, of course, that, well, to visualize such large data sets, you have to run these tools in parallel. So they scale beautifully to, tens and hundreds of thousands of CPU cores via MPI. But of course, you can download both Paraview and Visit on your laptop, and they work completely fine as standalone programs as well. So you have a very small data set, then you can analyze it entirely on your computer. They're open source, both under active development. They're multi-platform. They support all sorts of input data types. So there are over 100 input file formats for each. All sorts of visualizations, so scalar, scale visualizations, molecular visualizations, volume renderings, lots and lots of different things. And of course, they support parallel I/O, and they're based on the visualization toolkit library that I mentioned earlier. So I'm going to show you many examples and live demos now with Paraview, and all of these things apply to Visit as well. So because I just don't have time to show many examples in both Paraview and Visit, I'll just stick to Paraview for the rest of the workshop. So I assume that well, in order to be able to do remote visualization, of course, you have to be familiar with Paraview basics, and there are lots of resources we have online. One of the best resources is just download the materials for the Paraview workshop that are available, that are linked from this slide. So bit.ly/Paraview zip with 2 P's, and they will download the slides, a very large set of slides and data sets and sample codes. All right. So we want to do remote visualization with Paraview. And these are the options that you have. So of course, one of the options, you can always download a small data set to your computer and analyze it locally, but this is not what we're doing today. So another option is to run Paraview remotely on the cluster. So log in with SSH-X or -Y flag. So that's X11 forwarding over SSH, and open remote windows. And we really, really discourage people from doing this, because even though this is possible, and I know that many folks still use this protocol, it's going to be very slow. So it's going to be not interactive at all. So even on a fast connection, graphics forwarding over SSH requires a lot of round trips, and it's just going to be much slower than other options. So much better option is a VNC. Well, VNC or any sort of remote desktop. So the idea is the remote desktop is that you log in graphically to a remote system, and that will give you a large window, a large desktop, remote desktop. And on this desktop, you can open multiple windows, including Paraview, and then you can do your visualization remotely. So my favorite way of interactive remote visualization is client server, because unlike in the previous step with VNC or remote desktop, With client server, all your tools, all your GUI is running locally, right? So there is no lag, and the only lag is when you're trying to ship, a lot of pixels or any large data sets to your laptop. But in the Paraview settings, I'm going to show you there's actually a setting that lets you control the threshold above which all rendering is going to be done remotely. So if you find that your connection is slow, you can actually adjust its threshold, and it's really very nice to have that kind of ability. And then finally, of course, if you do your interactive visualization and you convert it into a script, then you can just run the script via batch mode, submitting it, let's say, as a Slurm job. So a few words on VNC, well, remote connections. So we support there are several different protocols depending on the cluster, depending on the system in Compute Canada. So on most clusters, you can run a VNC server manually on compute nodes with SSH tunneling. So you would submit an interactive job. Inside this job, you would start a VNC server. Then you would organize port forwarding, and then you open a local VNC client on your computer, pointing to local port, some default number, and that will basically click connect, and that will let you open a remote desktop where you will see your visualization. So this works on pretty much any cluster, but it's a lot of manual steps. And on some clusters, we actually have more automated workflows. So on Gram, we have a special system called Gram VDI.computecanada.ca. So for this one, you can take your VNC client, compatible VNC client, for example, Tiger VNC, and just point it to a Gram VDI system. Click connect. It will ask for your credentials, so username and password, Compute Canada username and password, and then it will open a remote desktop. So in this case, I have a snapshot of a visualization where I'm using Paraview. And in this case, because Gram VDI has GPU cards, I actually switched to ray tracing with NVIDIA Optics backend. So the way you do this in Paraview is in properties, right here in properties, you scroll down, you will enable ray tracing, and then one of the backends, if you have a GPU card, and if you're using a compatible version of Paraview, one of the backends is going to be NVIDIA Optics, right? So this will give you a nice rendering on a remote GPU. So the third option is Jupyter Hub. We have Jupyter Hub running on Beluga. And the way you access it, you will simply, all you need to do, you don't need a terminal. You would point your browser to this address, jupyterhub.beluga.computecanada.ca. Click enter your credentials, so log in, and then it will ask you to submit, to specify parameters for your interactive job. So the idea is that with a Jupyter Hub server, will run inside an interactive job on the cluster, and inside a job on the cluster, and then it will. So one of the things you can do inside Jupyter Hub interface is open a remote desktop. So you'll see it will be one of the big buttons on your screen once you start your job via this interface, and you open a remote desktop, and then you can start Paraview, Visit, or any other visualization tool you want. So this is for remote desktops. All right, so I'm not going to show you any demos of remote desktops. I'm going to show you demos of client server setups. So Paraview, fortunately, like similar to Visit supports this as well. Paraview has this multi-component architecture where there's a data server that is responsible for manipulating your data, so applying filters, decomposing your data set, et cetera, et cetera. There is a render server that does rendering, and then there is the GUI client, right? So when you run Paraview on your laptop, all three components are part of the same program. But in principle, all these three components can run on three different machines. So typically what you do when you do parallel remote visualization is you run the data server and render server as one application that is called PV server. Then you run the client Paraview GUI on your laptop, you link the two, and then you do all rendering remotely, but you have full impression that all your rendering is done locally because all your GUI is local. So time for the demo. We'll start with a very simple demo. So this demo is actually, the idea here is that we will do local debugging on a local data set. So the idea is the data set is so small that it can actually fit on a computer. And in the follow-up demo, I will show you remote rendering on a larger data set. So here we're going to do local visualization in standalone Paraview. We'll use the recording tool the trace tool to create a script from scratch. Then we'll simplify the script. We'll modify it to create animation. Then we'll copy the script to the cluster, run it there on a login node, and then I'll show you how to actually properly run it with a serial batch job. All right. So for this visualization, I will use a data set that I often use for training. It's called a sine envelope wave function inside a unit cube. It's just this mathematical function. So mathematical function of x, y, and z inside a unit cube is going to be discretized on a 100 cube Cartesian mesh. And in the so at the link here below, so the link that I mentioned at the beginning of this webinar, I have a zip file with a script generate sine envelope.py. So it's a Python code to generate these data sets. So if you have Python and an SCDF library installed, then you can easily generate the data set. If not, then you can also find these NetCDF data set inside the zip file at this link, right, under the data directory. So anyway, what I'm going to do is I will load this data set inside Paraview 5.8 on my laptop. So standalone Paraview, no client server yet. And the reason I'm using not the latest, not 5.9, but 5.8, because I want to match the 5.8 version we have installed on the cluster. Then I'm going to start the trace. I will load the data set. I will switch to volumetric rendering, edit the transfer function and the color map. Then I'm going to save it as a PNG file. Then I'm going to stop the trace. And then I will edit this trace and it will add some animation, right? So right now I'm working entirely on the in my local Paraview. So I'm going to go to Tools, Start Trace, accept the default. So now we are recording all the actions, and I'm going to go to File, Open, and then I will load the sine envelope.nc. So .nc is a netcdf file function. It's a netcdf file, so I choose netcdf reader, hit Apply. And here's my data set loaded. So it didn't complain. It shows the outline, right? So I know that it was loaded correctly. Now, what I'm going to do is I'm going to switch to volumetric rendering. I'm going to spin it a little bit. I'm going to edit the transfer function. So edit color map. And here I'll just modify the transfer function that it shows only high values of density. All right, so something like this. And then I'm going to switch to a different color map. Sure, it's not shown in red, but something that you might like more. For example, let's try this rainbow desaturated. Well, actually, it's red. Let's try warm to cool, this color, right? Okay. And then I'm going to save the animation, save the screenshot. So I'm going to File, Save Screenshot, and then save it as a local file. And I'll just give it some random name. Well, I'm going to call it cube.png into the current directory, right? Oops, cube.png in the current directory. All right, it asks for resolution. Let's say I want to save it at 800 by 800, and then image file format, and then compression levels. So I'll just accept the defaults. I'm going to say OK, and it was saved, right? So now I'm going to go to Tools and then Stop Trace, and it will give me the Python code behind what I just did in the GUI, right? So I'm going to save this. I'm going to go to File, Save As. And I will save it as, I'm going to call it volume.py. So I'll override the previous volume.py. And then I will open, actually, I'll need to open the text editor for this because I'm going to add this file. So I'm going to open a volume.py that I just saved. Oops, that I just saved, make it a little bit bigger, the font. All right. So you can see it nicely. And this is the script that I just produced using the trace tool from scratch, right? So you don't need to know any Python to actually do this. And let me simplify it a little bit. So I'll erase the comments. I'll erase a bunch of things. So the idea here is that the trace tool records everything, even the defaults. And a lot of these things you don't need to really do because they are defaults that will be implemented anyway. So I know a lot of things can be erased. So I can simply load the data set. And then I create the render view. I don't need the layout. So when you delete things, be careful, because if you delete things that are actually necessary, your script won't work, right? So a little bit of practice helps here. And basically the idea is actually a lot of these things I probably don't need. So let me comment these guys out. I'm just not 100% sure if I can delete all of them. You can certainly delete a lot of comments and so on. So the idea here is that you simplify your script. So here's materials library, something that is used for Osprey ray tracing, and we're not using Osprey right now. So I can delete these guys and so on, right? So the idea here is you can simplify your script drastically. And probably the last thing that you want to have in your code is this, where you save the file. And I'm going to call it new.png so that when I run the script, you actually see that a new file, new.png, should be created, right? And so here we are switching. You can actually see the lines where switched to volume rendering. So here we're switching to volume rendering, and here we are rotating. So these lines rotate the cube, and then we save the screenshot, right? So here we simplified our script. Let's just run it. So to run this, there are actually multiple ways of running this inside Paraview. One way is you can do it entirely from the command line. There is a tool called pvbatch in Paraview that you can find depending on whether you're on Linux, Windows, or Mac. You can find in different locations. So on Mac is typically going to be under applications. So what I'm going to do is I'll actually close this Paraview entirely. I just killed Paraview. And I'm going to go, I'm going to say applications, and then Paraview is 5.8. And it's inside the binary directory. It's called pvbatch. And to this, I'm going to pass my script that I just created in my, edited in my text editor. And then if it runs, hopefully it runs, it should produce a file called new.png. So if I do ls -t, you will see there's a new file called new.png. I open it, and it opened on a different screen. So let me move it here. So here's a file I created completely offline without opening any windows, right? And now I can do the same inside on a cluster, right? So all I need to do, excuse me, what I do, well, actually, I can modify the script to create some animations. Because we don't have a lot of time, I won't go through the details. You can study these details on your own. But the idea is that if instead of saving a single screenshot, you want to create an animation, what you do is you replace the save screenshot command by this loop. So in this loop, you're running through 90 iterations. And then at each iteration, you're saving into a file called frame, then 4 digits, specifying the number of the iteration. .png, and then later on you can merge all these PNG images into a movie. So I already created a file called volume2.py that I included into the zip download. So let me open it inside in here. So volume2.py is much simpler. So it's a cleaned version of the previous script, and where instead of the save screenshot command, I have the have this guy, right? So if I copy the script to the cluster, let me just copy it. Secure copy, volume, oops, excuse me. Secure copy, volume2.py to my username at cedar.computecanada.ca, and I copy it into the Scratch folder. All right. Okay, it copied. Then I want to copy the sign envelope function as well. .nc, so the data set. And this will take a few seconds. All right, so I copied the data set to the cluster, and I copied the clean script to the cluster. And then I will log into Cedar. I will go to the directory, Scratch directory. All right, I'll go to Scratch directory, and here are my files. I'll actually copy both files to the webinar directory. Overwriting the defaults, I go to the directory, and here I want to run pvbatch. So to run pvbatch, what I want to do is to load, oops, module, do it again. I want to load, oops. I want to load the Paraview module, and I don't remember its name. So what I'm going to do is just search for my history, and I will grab for module command. So yeah, I want to load this module, Paraview off-screen 5.8.0 module. And loading this module actually gives me access to the pvbatch command. So when I run pvbatch, I will need to pass the name of the script to it, right? So the script is volume2.py. And the script will run, and it will create 90 frames. Let's see. Not allocate memory. Oh, okay, interesting. So I'm trying to do this on login node. I'm actually running out of memory, which is actually a good thing to see. happening, because what you really want to do is you probably don't want to run this on the login node if it takes a fair bit of memory, a fair bit of CPU power. So running the script will probably take a few minutes, but still you don't really want to do this on the login node. You probably want to submit it as a batch job. So to submit it as a batch job, you would need to write a script, and in the script you will specify what you're doing, right? So in this script, I'm asking for 5 minutes maximum runtime. I don't need a lot of memory, so 3,600 megabytes is more than enough. Here I load my Paraview off-screen module, and here I actually run the script. So the script will produce 90 frames, and then I will right inside here. I'm using FFmpeg to merge these frames into a movie right inside the job. And then I remove all these frames because I no longer need them. So when I run the script, you will actually have the end result is going to be this movie, MPEG-4 movie, that you can download to your computer and watch it there. All right, so how does it do this rendering on a GPU-less node? So we didn't ask for any GPUs, we just asked for a basic CPU node. Well, the answer is this Paraview module was compiled with off-screen OS Mesa rendering built in. So basically, it will do all rendering in software, which is great because for that you don't need a GPU, and it's going to be fast. It's actually quite comparable to GPU speeds in this case. So I'm going to skip this example because this example actually somewhere intermediate for medium-sized data sets, and I will go straight to the large example because we don't have a lot of time. So in this case, I'm going to try to do interactively a very large example, show you a large demo. And I don't know if this will work on CEDA or not, but I also have a backup. So let me try to do this slowly. What we're going to do is we'll try to debug, visualize a very large remote data set, and we'll create a script. Then I'll show you the script. I'll show you how to edit the script briefly. And then I will show you how to actually run it inside a batch rendering job on CEDA. All right, so the data set I'm going to process is actually from the 2019 Visualize This compilation. So we ran a couple of years ago, and it's a fluid dynamic simulation of airflow around a turbine blade. So it's an airfoil, and you have some turbulent flow at the end of this airfoil, so this detachment region, right? And then a lot of turbulence. So the data set is very large. It is the numerical simulation was actually run on 512 cores. There are 5 hydrodynamical variables, and the data set itself, so all time steps, 86 time steps, is almost 1 terabyte in size. So if you want to visualize just a single time step, it turns out that loading the mesh plus a single time step requires about 200 gigabytes of memory. So obviously this you cannot do easily on your own computer. You need a remote visualization for this. And what I'm going to do is I'm going to actually start an interactive job using 128 CEDA nodes. And I will try to do it interactively in client server mode. And then I will create a script, and then I'll show you how to run the script via a batch job, right? So what I want to do is so I'm already on CEDA. I will submit, I'll say salog, submit a job asking for 128 CPU cores. I'll ask for 30 minutes, and then for 3,600 megabytes memory on each CPU core, right? So 30 minutes, 128 cores, and then 3,600 megabytes of memory. So let's see how long it takes for this job to start. And if it takes longer than a few minutes, then I have a backup cluster, so a training cluster where we might be able to do this as well. All right, so while it's starting, let me show you these steps in the slides. So what we're going to do is once it starts, I get an interactive prompt where I can load my Paraview off-screen 5.8 module. I will start the parallel Paraview server on 128 cores. And then I will, so it will be waiting for an incoming client on a given port on a given cluster node. Then I will need to organize SSH port forwarding to this particular port right here. This is the local port, Paraview port. This is the remote Paraview port. And this is the node where Paraview server is waiting for an incoming connection. And then on my laptop, I will start local Paraview 5.8. So it's important to have the same major number, 5.8, not 5.9. And then I will connect to port 11111 on my computer, and hopefully that will establish a client server connection. So let me check on the status. Now it's still waiting for resources. So then I'm going to enable the trace tool. I will open the my data set. So it will open just the very first, by default, will open the very first time step. It's important to say, set the keys type to decompose. So the idea here is that this particular simulation was run on 512 CPU cores, and each CPU core saved to a separate file. So it's decomposed in the sense that it was broken into 512 pieces, and this is the way the data is stored in the file system right now. I will apply the calculator filter to compute the magnitude of velocity. I'll call it speed, so this is speed variable, and then I'll apply contour filter at this value of speed, colored by the Y component of the vorticity, change the color map, save the image, and then stop the trace. So let's see if things are, yeah, looks like things are progressing. So now I'm inside the interactive job, and I have 128 CPU cores available to me. So what I'm going to do now is I'm going to say module load to load the Paraview module. And no, not this one. What I want to do is, let me just copy from here. So I'm going to load the Paraview off-screen module. And then I'm going to start the PV server, Paraview server on 128 CPU cores. And it should, if it starts properly, it should tell me that it's waiting for connection, incoming connection on a given port, given node. And in a different, oops, not this one, in a different window, I will need to organize SSH port forwarding. So here it is, accepting connection on this node 1132 on port 1111. So on a different, in a different terminal window on my laptop, I need to organize port forwarding. So this is going to be connecting to the node 1132 on CEDA. And here now the two ports, oh, actually, sorry, not this one. I need to, sorry about that. I need to, this is bad. I had a typo here, not, it should be not 2, but 1. So let's see if I can cancel this command. What I want to do is local port 111, right? This local port to this remote port, I'm connecting. Okay, and now the ports are connected. And what I'm doing now is I'm starting Paraview 5.8, so the same major version. And then I will connect to local port 111, so this one on my computer. So let's see if it works. And inside this window, it should say, yeah, client connected. So now we have successfully established the client server connection. And now, so now I go to File, Open. And now this is the remote file system, right? So this is the file system where I'm on Scratch disk on CEDA. I'm going to go to Airfoil and open the keys foam dataset. And here, before I hit apply, I need to say keys type decomposed. And now I can say apply. So now we're loading the data set. And by the way, I forgot to enable a trace tool, but you should, so if you want to record your workflow as a Python script, you want to enable the trace tool before loading the data set, right? So this is something I forgot to do, obviously. I'm not going to redo it now because we have only 10 minutes left. So now we loaded the data set. Okay, so here's the data set. It's actually a large data set, right? So it requires roughly 200 gigabytes just to load a single time step with the mesh. And what I'm going to do now is I'm going to apply the calculator filter. So I'm going to compute a new variable that I call speed. And then it's going to be a magnitude of velocity. So velocity is one of the scalar field, one of the fields, actually vector field, yeah, velocity, oops. Magnitude of velocity vector field. So I want to have the absolute value. So hit apply. This should take a few seconds. So now my data is decomposed. So actually processing the new variables computed in parallel on all 128 CPU cores. And then what I'm going to do is I'm going to bring up the contour. And I'm going to contour by the speed. And the value is, yeah, 0.8 is fine. So this value, I'm going to say apply. Again, it will take a few seconds. Now it's actually doing rendering contour in parallel. So here I have, let's see, you can see here the turbulent flow right here, right? And we're doing rendering now in parallel. And then I'm going to call it by the Y component of the vorticity. So call it by the Y component of the vorticity. And then I'm going to switch to a different color map. So I like this color map because it just shows a lot of distinct colors. Here we go. And then, so here we have our visualization. And then I'm going to File, Save Screenshot. And so when you see the screenshot, this is actually my local file system, right? So even with client-server remote rendering, this screenshot is going to be saved. I'm going to call it remote.png. It's going to be saved locally, so into a local file. I'll just accept the defaults, right? And so here the idea is that what I did, you actually need to wrap into the trace tool. So before doing visualization, you would go to Tools, Enable Start Trace, and then you finish your visualization, you save it into a file, the image into a file, then you go to Tools, Stop Trace, and then that will give you the Python code, and then you can save this code locally, Python script locally. You can edit it inside your text editor, so simplify it. Then you can copy it to the cluster, make sure that the directory paths and the file names are specific to the cluster, so you should edit them, change them from your local file system to the remote file system, and then you have a script that you can submit on the cluster, right? So the script is going to be, you can run it. So you have the script, let's say you will call it airflow.py, and actually inside the zip download, I gave you a copy of the script, so you have this guy. You can actually try to run it on your own after the workshop if you have a Compute Candidate account. So here we copy the script to the cluster, right? And then in this case, I simply submit it as an interactive job, right? So I call Salog. I ask for 128 CPU cores, this amount of memory per core, 60 minutes, and then inside. So once I get a shell prompt inside the interactive job, I load the Paraview module, and then I call PVBatch in parallel and pass this script to PVBatch, and then it will do the all rendering without opening any windows off screen, right? And so once you're happy with the result, it does what you want to do. You can actually submit it as a batch job, right? So instead of Salog, you will submit it with as a batch job. So we have only a few minutes left, and I really want to talk about a few other very important things. So one of them is data partitioning in parallel Paraview. So Paraview by default will automatically partition your structured data. So that means that if you're loading image data, you're loading a Cartesian map, basically any of these file formats, so structured points, rectilinear grid, or structured grid. So basically Cartesian meshes, curvilinear meshes, all of them will be loaded. So if you have a single file, not parallel, not decomposed, but a single data file, and you load it into parallel Paraview, it's going to decompose it automatically. So it's going to break it into pieces, and then each piece will go to its own CPU core. So, however, you might run into bottlenecks because you're reading this data set in serial on a single core, and then by message passing, it sends various chunks to various cores. So if you run out of memory on your reading core, then obviously most likely what will happen, Paraview will crash. So you have to keep that in memory. Oh, sorry, you have to keep that in mind. And so there's a way to solve this. I'll mention it in a minute. With unstructured data, Paraview will not decompose it automatically. So if you read your data, your serial data, into parallel Paraview, and if your data set is a bunch of points or polygonal meshes, data on polygonal meshes, or data on unstructured meshes, Paraview will read it in serial and will keep it in memory on the single processor, right? So to actually be able to process this data and render this data in parallel, what I want to do is you want to pass this data through a filter called D3. It's called D3 in Paraview. Stands for Distributed Data Decomposition Filter. And that filter will actually break this data set into pieces and then will ship this via message passing to other CPU cores, right? So now your data set is properly decomposed in memory. So now what you can do with after passing data through D3, you can actually go to File, Save, and save it as a decomposed data set. So if you're doing this, let's say 128 cores, when you try to save it as a decomposed parallel data set, so in this case, with unstructured meshes, is going to be a PVTU file, stands for parallel VTU file, is going to save this file, actually is going to save this data set into 128 individual files plus one metadata, one header file, right? And so the next time you read this data set is actually going to be fast. So the next time you read the parallel PVTU file, files, it's going to be much faster than a serial file. So the same applies for decomposing data sets, and saving decomposed data set applies to structured data as well. Let's say if you have some huge, let's say 10,000 cube Cartesian mesh, and reading this mesh just takes a long time, even from parallel Paraview. Well, what you need to do is you need to decompose this data set. So if you know that in the future, all you're going to do is analyze this data set on 16 cores, you need to decompose it and save it as, break it into 16 pieces and save it as a decomposed VTI file. So there's a special format in VTK. PVTI stands for parallel VTK image data. Right. So here's an example. I just did some timings 2 days ago. I took a large, so 9 GB data set, which is a serial VTU, so unstructured mesh data set, and I tried to read it into parallel Paraview on 16 cores because it's not a decomposed data set. It will read on a single core, and then it will automatically, then I pass it through D3 and will distribute it to all cores. And so reading it in serial actually takes almost 2 minutes. So after this is done, I pass it through D3, and then I go to File, Save, and save as a parallel VTU file. So it's going to save it into 16 files plus one header file. And I also enable compression. So compression is always nice to use if it's available. So I enable, relatively mild, so fast compression. And this saved it in 70 files. So now I have a statically decomposed data set. Then I restart my parallel Paraview. So I just start from scratch on 16 cores, and I read it on 16 cores, the same PVTU data set now in parallel. And my reading time, instead of 2 minutes, is now 11 seconds, right? So there's a huge speed up. And this is going to be, more and more important if you go to large and large data sets, data sets that are in the terabyte territory. Of course, you have to store and read them in parallel. You just won't be able to process them in serial. All right. So how many CPU, GPU cores do I need? Also, another really important thing, almost the last thing I'm going to mention. What I recommend you to do is, if you have a large data set, you really want to look at the data set size, and then that will be the guiding factor in how many CPU cores and how much memory you want to use. So let's take the example of CEDAR cluster. So in CEDAR cluster, the base nodes have 32 cores and 128 gigabytes of memory each. So that means that roughly you have 4 gigabytes of memory per CPU core on CEDAR, right? So when these cores, each core is running Linux. So that means that some part of memory is taken by the operating system and by various utilities. So probably for your rendering, you have 3.5 gigabytes of memory per core available on average. So this is the number that you will start with, 3.5 gigabytes per core. Let's say you have data set that takes 200 gigabytes in memory loaded, right? So the example that I showed you a few minutes ago. So taking 200 gigabytes dividing by 3.5, you get 58 cores. So 58 cores, well, basically it's close to 64, right? So close to 64 cores, because you need to account for some MPI buffers, filters, and so on. So that means that on 64 cores, you'll be able to barely process your data set, but you won't be able to pass it through any complicated filters, because filters also might take a lot of memory. So to be comfortable using these data set, processing data set and visualizing, you really want to be using 128 cores on CEDAR, right? So that's why in the example a few minutes ago, I started the job on 128 cores. And yeah, so and then everything is determined by your data set size. So rendering on GPUs is possible. So what you do is, we have a special compiled version of Paraview called Paraview Offscreen GPU 5.8, and it was compiled with EGL support. So EGL stands for Embedded Graphics Library, and it's part of the NVIDIA driver that lets you do rendering directly on the GPU without opening any XLN windows, right? So rendering context, so the surfaces are provided directly by EGL. And it works great. So until recently, we had some problems with it, but fortunately, the problems are now resolved on all clusters. And yeah, all you need to do is basically, you will run the same script, the same Python script, for your rendering, but you will, instead of loading the Paraview GPU module, you will load the Paraview off-screen GPU module. So should you use CPUs or GPUs for rendering? I'm very partial to CPUs, and the reason is because we have a lot more CPUs than GPUs, so it's much easier to get, let's say, 100 CPUs than a few GPUs, right? Because GPUs are in very high demand, and there are sort of so few of them. So for CPUs, there are a number of really good libraries that we have built into Paraview and other tools as well. So things like Osprey or Mesa, and they do rendering entirely in software without needing GPUs. And the thing is, when you already have a lot of CPUs allocated to your job, and you have large data sets that barely fits into memory on all the CPUs, you already have all the CPUs available to you. So why not do rendering in parallel as opposed to also involving GPUs? So that's my reasoning for preferring CPU rendering for large data sets. But of course, you can do GPU rendering as well. So if you want, you can try doing that. All right, so everything I said applies to Visit as well. So Visit supports Python scripting, supports MPI, everything I showed, but things will work differently. So we have on our Viz pages page inside the training module, so all the links that I provided you before. We have some links to Visit workshops as well. So if you're curious in how to do all this stuff in Visit, there are links, so we have material. And I think what I'm going to do is I will just show the summary page, and I'll mention that next week we're going to teach hands-on national Paraview workshops, and there are still spots available, so registration is open. It's going to be next Monday and Tuesday, 3 hours, so starting at 10 a.m., finishing at 1 p.m. Pacific time, but it's open to everybody in Canada, well, all students, postdocs, and faculty in Canada. And yeah, and I will stop here for questions.